As we heard, next talk is Harry Miley, who's going to talk about a gamma-gamma coincidence detection system for radionuclide aerosol monitoring. Please, Harry.
Thank you. It's great to see all you folks out here today. And it's great to be here. But I'm giving someone else's talk, and that's always hard. So I will probably not do good justice to Alex Couture's talk. I'll just talk about the things I want to talk about instead. But this does follow on very closely with all the things that Michael was just talking about. And of course, I wanted to jump up and say, but wait, there's more. So why don't we go ahead? We're talking about now the radiation detection part that follows behind the collection part that Michael was talking about. Next slide, please. Or do I do that? This great big button that says next. So Alex included one graph here of that says why things are better when we take more samples. And in this thing, green is good and orange is bad. And what he's showing is that if we did a 12-hour sample instead of a 24-hour sample, that we would start filling in the tropic zones with sensitivity. That's one of the weakest points in IMS radionuclide monitoring is the tropic zones. The air moves more slowly and so forth. But there's probably a dozen other charts where we've said, oh, well, we'll get more samples are detected, or we'll get more stations that report, and so on and so forth. There's many benefits, and we're only showing one here. So he does say the objective is to maintain the IMS requirements with shortened collection and counting intervals. And counting is jargon from our field. That means measurement time if you're not a radionuclide person. So Alex says, our proposed solution is a gamma-gamma coincidence system. I wouldn't have said that. I would say a dual germanium detector system, which you can do coincidence with. Okay, on we go, and I'll fill in all these details as we go. Oh, and it's me again. So, Alex is showing here a balance between competing trends in your sensitivity. So in the center, it says collection per count time or versus count time. So if we have a longer count time, we're going to have a lower, better MDC. But unfortunately, when we say we want to go to more samples per unit time, we're not going to have longer count times. We're going to have shorter count times. So that unfortunately will push our MDC upward, which is not good. But at the same time, we nuclear types were just saying, hey, Criari, flow more air, lots more air. And if we have more air, then our MDC comes down. Okay, so we're balancing flow rate with the collection time and counting time. And now, Alex has created this three-color chart, and it does actually help explain something. The top one, green, yellow, and red, are the three phases of an aerosol sample today that are done in the IMS, where we collect for 24, decay for 24, and measure for 24. And what would this look like if we did 2 samples per day or 3 samples per day, even to the rather crazy 12 samples per day? And you could see we collect for a very short period of time, decay, 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 and then count for a short period of time such that we maintain the overall 72 hours from the IMS operations manual. Now, this works if you can move an arbitrarily large amount of air with high efficiency. Okay, so on one hand, there's more air. It works if you have longer longer decay time, and it works if you have much more detection efficiency. So the sweet spot here that's doable might be 3 per day or 4 per day, but we'll carry the rest of those along in our calculations and so forth as we go forward. And just as a quick reminder, this is what the RASA, as it is deployed in the IMS, looks like. It's a system that brings in 6 strips of filter paper. The air goes through the filter paper and then wraps around the germanium detector. Okay, and as Michael just showed you, the ESP collector, I describe it as a set of organ pipes. These are square pipes, in an up and down orientation that the luminized mylar comes through, and we collect on the mylar, and then that's brought out through the thing, which I didn't hear Michael call it twirly, but that's the name for this thing that spins the sample up and gets it between the detectors. And a look at what the detectors will look like is on the right. That's dual detectors. Most of the time you would be in just summed singles mode. Just add the two detectors together to analyze. And so it'd be the same analysis that you do today in the IDC. I won't spend any time, all of Alex's great work on modeling, except the fourth bullet from the bottom, which is, I think, very innovative of Alex. He made a cost per sensitivity figure of merit and said, what detector will give us the biggest bang for the buck, and selected it. And honestly, much better than the analysis I had done a year or two before that. We've got a system built. It was built by John Burnett, if anybody knows John. A system built that allows us to do the multiple gamma summed singles or coincidence measurements so that we can do software development, analysis, and control. And there's been quite a bit of that. The only part of this that I really want to talk about is the very last bullet, which up until this point we haven't mentioned, that we plan on having a first look detector that's looking at those organ pipes as the air is collecting on the inside. So we might have a trigger that tells the Ch3 folks, it tells the collector, slow the flow down, reduce the efficiency, because we have a tremendous Fukushima-like signal coming in. We don't want that much radioactivity, or something. So we have an early look detector that will be part of the system. And in terms of software development, really what I want to focus on here is in the upper left here, you see a normal gamma singles, what we call a spectrum, and the individual peaks you see in that are indicative of specific isotopes that will be on the filter, most likely natural radioactivity. In a two-dimensional display, if you look at the coincidence between the two detectors that might occur within about a 2 microsecond period, you would see this two-dimensional data, and where those lines cross is where the actual coincidence data, nuclear data, exists, and you can throw everything else away. So it's very, very powerful. You've heard xenon people talk about this before, I'm sure, but they didn't invent the idea. They've just been using it very successfully to reduce their background by a factor of 10,000. So that could work for us, but the analysis is more complex, and so you're probably going to do it only for special samples where you've had a seismic trigger or some other tip-off that says these samples are more interesting, because it'll take longer, it'll take more analyst time. The point that I would like to point out on this slide, I know it's here someplace. Yes, the near-term plan. Model RASA 2.0 geometry, done. Calculate the efficiency for barium-140, iodine-131, and moly-99, done. Estimate ambient and sample-induced background in all the IMS stations in the network. And that is one that Alex has been working on just in the past week. And it's actually turned out to be very interesting. And we may find a way to optimize our detection that we have never thought of before. It'll have something to do with our shielding or something like that. And so this brings us to the end. The next steps, an air collection campaign to assess the background versus decay time. What does that mean? Ch3 has kindly made for P&L a single organ pipe so that Alex and company can take a fresh sample and immediately count it. And they think that some crazy guy wrote this MDC equation a few years ago, that's me, and that it might be wrong, and let's see if we really need to do all the decay that's necessary according to the MDC calculation. Also evaluate RASA 2.0 for an extended set, let's say all the IMS radionuclides and so forth. So Alex has lots of work to do on the detector-only part. But the part that isn't obvious, but I think Michael touched on, is we've got a detector sitting in Washington State, and we've got a collector sitting in New Hampshire. And these things need to be in the same room, and we need to start, actually running the major subsystems together so that we can finish. Okay, well, with that, I'll turn back over, and I'm record-breaking for me, 2 minutes short of the mark.
Perfect, Harry. Thank you very much. Okay, questions to Harry? Peter, use the mic.
Thank you very much. So you talk about simulating the MDC, and that should require simulating the efficiency to the nuclide of interest and also the background. But the background in a coincidence setup is sort of complicated. How do you go about to what is the model you use to simulate the background?
Okay, excellent question. And the answer is we've, so far, the old guys have done all of this assuming summed singles and no coincidence. So we've taken the actual numbers from the actual IMS stations that say what their MDC is, and they also say what their lead-212, et cetera, content is. So that's how we've done it so far, and have not done the coincidence, and that's yet to be done by Alex. So we are wrestling with that, but I think he has all the parts he needs to get there.
Thank you.
Mm-hmm.
Any more questions? Okay, I can't see any more, so thanks again, Harry.
When will it be finished? Okay, when will it be finished? I heard somebody ask. It depends on funding and so forth. But the point is, and I'm not with P&L anymore. I'm just an advisor to DITRA on this. The point is, the two teams have gotten to very reasonable TRL on the major subsystems. The twirling thing is the lowest technical readiness level thing that they have, and they need to get these things together, and they're very close. Okay? It's all right.
Thank you.